was 1, right? Of course, the x-intercept also happens to be the point of tangency in this example. And the equation is 2 times x minus 1, which you could multiply out, right? If you don't like this format, you could also write that as what? 2x minus 2, right? Either is a fine answer in my book. 2x minus 2 is nice because it shows you that the y-intercept of this tangent line is minus 2. So, about down here. And I'll graph the tangent line in red. There you go. This is the tangent line. 2y equals f of x. Yeah, a equal to 1. Well, I mean, I could be more specific. It's, of course, x squared minus 1, you know. What is the tangent line? What's the significance of the tangent line? It's telling us how the function changes at the point 1, right? So definition, by the way, L f a of x is equal to f of a plus f prime of a times x minus a is the linearization of f of x at a. Now, the linearization doesn't always exist, right? I mean, there are functions we're going to talk about next time, not today, but we'll talk more about this next time. There are functions for which the derivative doesn't exist. Like this difference quotient we calculated here, it doesn't always have to work out. There are functions where this doesn't actually converge to something. It doesn't have a nice limit. All right, and for those functions, I can't calculate the linearization. But linearization is just a fancy name for it's the function whose graph is the tangent line. And the linearization of a function, it's the best linear approximation to the function at the point. That's what it is. If I want to replace a curvy function with a straight function, that's what this does for us. That's what the derivative is all about. It's about replacing some curvy thing with a straight thing, because straight things are easier to think about. Sometimes we like to calculate the derivative at an arbitrary point, right? So remark, by substitution, we can also express f prime of a. All right, so f prime of a equal to what was it? It was limit as h goes to 0 of what? F of a plus h minus f of a over h. So what if we make the substitution x equal to a plus h? What happens then? If I want x equal to a plus h, that means also what? H equals to what? X minus a, right? So this becomes the limit as x goes to a of f of x minus f of a over x minus a. So this is an alternative way we can calculate the slope of the tangent line. If you'd rather do a limit in terms of x, you can do this. But then instead of taking a limit at 0, we have to take a limit as x approaches a. You know, which is easier. It depends on the problem, honestly. Some problems, the one thing that makes this maybe A nicer approach for some people is like you don't have to think about function composition as much, right? That was kind of a wrinkle, a fly in the ointment in the last one, is we had to understand what f of 1 plus h meant here, right? If we look at the tangent line, the slope of the tangent line this way, we can just plug in x and plug in a. People are less likely to get into trouble, I suppose. That's one merit of this. So let's look at that. So again, f of x equal to, let's do x squared minus 1 again, right? And let's find the slope of the tangent at 1. So I'm going to be a little bit more abstract. Rather than doing the derivative at 1, I'm going to do the derivative at a for like an arbitrary a. So we do limit as x goes to a of f of x minus f of a over x minus a, right? What is f of x here? What is f of a? We've got x squared minus 1. That's f of x, right? What's f of a? A squared minus 1, right? And so you guys tell me. I want your honest opinion. That thing I just wrote on the board, is it good? You honestly don't know. Mm. Right, but, well, that's what we'd be tempted to do, and that would be wrong. The reason it's wrong is because I didn't put parentheses in. See, it's minus f of a, right? So that minus attaches to everything in the formula for f of a. And if I don't write parentheses here, I'm going to be tempted to think about it like you just said, which is like, that's the danger here. We have to remember that that minus goes for the whole formula of f of a. So in fact, those we should do what you said, but there's no 2. The minus 1 and the minus minus cancels. And so we've just got limit as x goes to a of x squared minus a squared over x minus a, which is the limit as x goes to a of x minus a times x plus a over x minus a, which we can cancel. Cancel the x minus a's. X plus a, limit as x goes to a is what? Plug in a, we get a plus a, which is 2a. 2a. So the slope of the tangent line to f of x equals x squared minus 1 at a is just 2a. This is totally consistent with our last example. We just do what? Put a equal to 1 and get back to the previous example. This is a kind of funny thing. What's more trouble? To calculate the slope of the tangent line at a specific given point like 1, or to calculate the slope of the tangent line at an arbitrary point a, it's the same calculational trouble. So as a general point of order, I try to mostly just focus on how to calculate the tangent at an arbitrary point in as much as I can help, because it's just the same trouble. Why not do it for every point rather than just one point? This too, plug in, so I get equals limit as x goes to a of x plus a, which then, when we take the limit, we get a plus a, which is 2a. Yeah. So I didn't drag out the discussion of tangent lines today that long, because I spent like 10, 15 minutes talking about it at the start of the limits chapter. So if you're rusty on that, you might go back and like click on some of the visualizations in the notes. We'll do more of it Friday, actually. Friday we actually do have a lab. We'll be across, and the lab Friday we're actually going to like look at how to make some tangent lines in probably Desmos, possibly GeoGebra. We'll figure it out when we get there. So I'll see you guys Friday. Oh, yes, if you haven't already given me your homework, please do.